Okay, good morning, everybody. So let us start our lecture today. Today is October 21. So before we start, there are a few announcements. Let us see our schedule first. So according to our schedule, your test 2 will be next week, right? Test 2 will be next week.
Do you know if it will be Tuesday or Thursday?
Yeah, let us make it next Thursday. So a week from now. Okay. So next week, this time will be your test. And it will be in D2L quiz section. So and then in the test we will cover. So previously we covered until pointer, right? So this time we will cover linked list, tag, QE, and recursion. Okay, so we will cover linked list, stack, QE, and recursion. Okay, so and the test will be in the quizzes section, in D2L quizzes section. So I have started writing the test. So you will see in this October. Let us check that your time is okay. So your class lecture is class time is 11 a.m. I will make it open 15 minutes early, and then it will be open until 12:15 p.m. until at the last time of our lecture. So it should be good that if you start at 11, 12:10, it should be good, but please do not wait for the last minute. You may have some issue. Okay, so please take it during your class time. Okay, and by this weekend I will make the test, and then by the weekend or early next week I will make the announcement about I will upload a study guide. By the weekend I will upload a study guide. Okay, and I also uploaded quiz 4. So quiz 4 is due before your test. Okay, quiz 4 is up now and complete it before your test. So then when you complete the quiz, then it will be review for your test also. Give me 1 more minute, please. Okay, so okay, so we will have 5 to 6 quizzes during the semester. So okay, this will be our 4th quiz, right? Okay. Give me one. Okay, so now let us go to our lecture. Okay, so we are discussing trees. So a tree is a non-linear data structure, right? So as we discussed, as we started our tree discussion last week, so a tree is a non-linear data structure. Let us do a quick review. So in a tree, the data elements are linked, okay, somehow linked together, but not one after another. So like a tree. So in natural, we see a natural tree like this. This is a tree root. Okay. So the root goes down in that, but we do not see. So we see only the up of a tree. So but it's our this kind of tree is upside down tree. Okay. So for instance, in a tree, this is a root. The top element is a root, and then we say the root has some branches. There maybe have one or more branches, two or three branches, two or more branches, 2, 3, 4 branches. But if a tree has maximum true branch for each node or each node, then that is called a binary tree. Our goal is to understand and learn binary tree. Okay. Also, there are different kinds of binary trees. We will move towards those. Okay, and these are node. If a node or the nodes that do not have any more child node, that are called leaf node. Okay, for a tree, branches as sub-branches. Okay, and then the top level of a tree are leaf, where there is no more branch. Okay, so although like this is not a linear data structure, but tree has many application and implication in data structure and in computer programming. We will see some of this. Okay, so in our last lecture we discussed a tree representation, how a tree is represented. For instance, we started with a tree, and you see that the tree, if these are character type data, so character type data are encoded with single code. Okay, so a tree, this is how a tree, okay, is drawn in a piece of paper. Okay, but in computer memory it holds either in a link with a linked list or with a with an array. So if it's implemented with an array, so that will be, for instance, a will be in index with index 0 root, and then next one you see that a, and then h l is coming here next one, and then g is coming here in the next one. Okay, then it will come o, then it will come here, and then r, it will come here. And so there are some rules then how the other elements will come. Okay, we will see this. So the rule of thumb is that here. Okay, these are the rules. There are several the rules. Okay, the data from the root always appear at with index 0 in the array. Okay, so the root will be always at index 0. And suppose that the data from the non-root node appears in the component I. For instance, we say that these are non-root. This is root, and then these are non-root. These are, say, denoted by I, okay, and the array. So the data for its parents is always located. Okay, so data for its parents is always located. This is for if I is a node, so the for ith node that, okay, parent data will be located as at I minus 1 divided by 2, okay, and with integer division, okay, and then integer division means you are taking the floor, okay. For instance, if I equal to 1, okay, for instance I equal to 1, so here I is not the root, except the root. For other than root will be always in at index 0 when we are talking about other elements, okay. So other elements, for instance ith elements, if I equal to 1, then 1 minus 1, 0 divided by 2 equal to 0, and that is the root. So for instance the first element, this one, its root, its father is 0, is root. How about the second one? If I equal to 2 for this one, right? Index is 2. I equal to, so this is 1 and this is 2. So then 2 minus 1 equal to 1 divided by 2, 0.5. But we are taking integer division. That means we are taking floor. Okay, that means 0. So the index 0 is the father of G also. Okay. This is how, using this formula, we can calculate for any nodes. For this node, for instance 5, okay, who is the father or parent of 5? So 5 minus 1 equal to 4. 4 divided by 2 equal to 2. So what is at root 2? Okay, so at 5 we see that at 5 we have I, right here I, and at 2, 5 minus 1, 4. 4 divided by 2 equal to 2. So at index 2, so 2 we see G. So G is the father of I. Okay. So by using this simple formula, we can find for any elements, non-root element, for any element, we can find its parent. Okay. Or since it is ceiling, you may see that you can write like this way: I minus 1. This is I divided by 2, and ceiling we mean like this way, floor. I'm sorry, this one. We can take floor. Let me get my pencil. Okay, is everybody okay for this one? The rule 3, rule 2. Now let us say that there's, let us see that if we know another way, if we know the the index of a node. Okay, then how can we find child index, the left child and right child? There are two children, right? One is left child, another is right child. So for instance, G, the left child is I and right child is T. Okay, the formula is left child is at component 2i plus 1 and right child is the component 2i plus 2. So for instance here for G, yeah, for G, okay, so left child is I, right? So here G's position is 2, right? Then 2i, that means left child, left child shamar equal to 2 times 2 plus 1 equal to fifth, index fifth. Okay, and right child index, right child index, this is the left child index equal to 2i plus 2 equal to 2 times 2 plus 2 equal to 6. So here right child equal to 6t is the right child and I is the left child and 2 is here. So these are the three formulas you need to remember. Okay, so this is why from in array implementation, whenever you know I index of an element that is non-root, for non-root is always index 0. Okay, this is root is always 0. Then if you know I, so then for I, having I, we can find its left child or right child, and also for left child or right child using this formula, we can also find its parents. So here both for 5 and 6, for instance, if 5 minus 1 equal to 4, 4 divided by 2 equal to 2. So G will be 2. Okay, and then 6, right? So 6 minus 1 equal to 5. 5 divided by 2 equal to 2.5. But we are taking floor over here. Then 2. That will be 2. Okay, does anyone has any question? Can you hear me?
Yes, I can hear you. No, I don't have any questions.
So now let us. So in our last lecture we discussed trees. Okay, so I don't know, maybe there is an issue. I could not download the file. It was not ready until yesterday. I checked. I will check today if the last file is ready. Then I will upload it. So in our last lecture we discussed trees and the tree properties. Okay, tree properties means these are the things that in our last lecture we discussed. Please review this, and we went through the examples. So degree of tree is degree of the depth or a height or ascendance, descendants, ancestor, path, whatever we discussed. Okay, these are the things we discussed. Okay, so we started a tree, for instance, in a naturally a natural tree can have many branches, and there is no formula. how the branches will grow for a tree, right? Okay, but in our programming, similarly, there can be many branches of tree, but so maintaining many branches is difficult, is a problem. So we usually use a tree that grows in a systematic way with maximum 2 branches that are called binary trees. Okay, and binary trees. So in a binary trees that has, again, there is a classification of binary tree. One of the binary tree is called binary search tree. So in the binary search tree, the left values are less than root values, and root values, okay, and is okay. So this is left value is less than root value, and also less than right values. And right values is always greater than the root. Okay, for instance, like here. So if I have a data set like it's coming data set like coming 10, okay, then 10, I'm putting 10 over here, okay, then I have another value, next value 12, then I put 12 on the right side. So we are developing a BST, binary search tree, okay, and then at the next value, if I encounter 8 is less than 10, so it come on the next side, okay, and if I face another value 6 is less than 8, so then it will go left side, okay, and if I counter another value 7, for instance 7, then 7 is less than 10, so it will come left side, less than 8, so come to the left side, but it is greater than 6, so it will go to the right side, 7 will go like this way. Okay, so if I enter another value, get 9, so 9 is less than 10, so it will come left side, and but greater than 8, so it will go right side here. Okay, so this way a tree grows. Okay, so this is called a binary search tree. So in the binary search tree, the root element is greater than left element, and it is less than the right element, and there is no duplicate element in a BST, in a binary search tree. Okay, but sometime it may happen, for instance, that we are fine. Okay. So this is the binary search tree. Okay, so the here height is pretty balanced. Okay, so here height will be 1, 2, and 3. So 1, 1, 2, and 3. So height will be 3. So 3 levels. Okay. Now, if I encounter a data set in different data set, for instance, I have data set 10. Okay, then let me kill this way 10. Then 10 I put this way, and the next value I put 12. So the 12 value goes to the right side, and the next value I get 14. The 14 will go this side. Next value I say 20, so 20 will go right side. And next value I say 25, 25 will go right side. And the next value, for instance, again greater than, for instance, 50, 50 will go right side. So here this tree is a BST. It is a binary search tree, but this is growing linearly. See that, like a linked list. It is growing linearly. Okay, so that is not efficient. For instance, your height will be here 1, 2, 3, 4, 5. Okay, but if we would get our data values something different, like this way, for instance 14, and then later come 12, then 12 go left side, later come 20, 20 go right side, next come 50, 50 go right side. Okay, and later come 10, so 10 will be on the left side. So here this is height equal to 3, and here height equal to 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So here linearly growing, and this is here is growing is logarithmically. His height will be Lz logarithm of n, and your height is n. Your height equal to n. 1, 2, 3, 4, 5, 6, and then 3 n. Okay, so big O n. Okay, so here this is a problem. This is a problematic BST. So this is not height balance. So there are some trees that is called ABL tree, okay, and then red black tree, okay, splay tree. These are height balance tree. Okay, these are height balance trees. So like this, so they automatically balance their height. So they do not grow linearly. Okay, so this kind of tree have advantages that they ensure that the complexity will be logarithmic time, not in linear time. Okay, so later we will see, maybe hopefully if we have time, then we will see ABL tree or red blood trees. Okay, but so today we will just cover binary search tree. So binary search tree is the foundation of many other trees, ABL trees, plate trees, red blood trees. Okay, like heaps. We will discuss this. Okay, so we discussed that a binary tree that has only 2 branches, and then full tree is the binary tree such that each non-leaf node has exactly 2 child nodes. Okay, and a complete tree is object level L such that it has all possible nodes. Well, for instance, this one. Let me give an example. So this is a full tree. This is a full tree, and this is a complete tree. Complete tree means here is by 2 branches. Each node has 2 branches, 2 child, and then if there is an additional child, that they will be filled up from left to right. Okay, that means if it gets one more additional node, then that additional node will go here with here additional node will go here, and the third node, another node will go here, and after this node, if there is another node, then it will go here, another node that will go here, another node that will go here, another node that will go here. So these nodes will be growing systematically from left to right. Okay, so this is a complete tree. But if We do not have this, but in some case it grows like this. Then this is a binary tree, but this is not a complete tree. This is an incomplete tree. Okay. And this is a full tree. Full tree means for all levels except the leaf levels. Okay, all levels have completed has completed all nodes. So if it did not contain this, then this will not be a full. This will be a complete tree, but this will not be a full tree. Okay. There are some examples over here. Go to this. In the last lecture I went through this, and then the last lecture, okay, I went through this today. How to find left child and right child levels. Okay, and then okay, for array implementation, as I saw at the beginning of this lecture, that for each node, okay, they put in a computer memory in some specific position. They cannot put randomly at any position, right? So that position that takes the here computer memory like this, and other values, other position, there are no values, so there will be null value. Or for integer type array, there will be 0 value. For string type, this will be null value. This is why this is signed as what? What sign that means? Based on the data type, it will. For integer data, default value is 0, so it will put 0. For string, it will put null value. Okay. And I gave you some homework to practice. Okay. And there is another implementation for linked list implementation of tree. So we will go both example of both linked list implementation and array implementation. Okay. And the last thing we discussed in our last lecture was searching. Okay, or traversing. Okay, on a binary search tree, there are there are mainly two kinds of traversal, right? One is breadth first search, level by level, and another is depth first search. That is 3 kinds. So the pre-order, that means the root or vertex, okay, is covered first, then left child, then right child, and the in order, the vertex, it goes in between. Okay, and the post order vertex, it goes all the way end. But you see that always left node comes first, then right node, left node come first, then right node, left and right. And you see, you will never see right first and then left. Does anyone has any question?
No questions.
Okay. So the book has algorithm, this has algorithm, so we will cover algorithm, okay, also, but let us see some, okay. Okay, so please practice this, okay, please complete this, like, so this is vertex, left, right, left, vertex, right, left, right, vertex. Please practice this, okay, and write down some. Okay, so okay, breadth first search is go one level. This is level by one. This is, for instance, first level. Complete this level. Okay. So this is one level, complete this level A, and then complete the next level, go B and C. So A over here, B and C together, and D, F, G, H, and D, F, G, H, this level. And I, J, K, I, J, K, I, J, K, this level. So we will come to a program later, but let us see what else we do have. Building expression trees. We're not going to cover this. Okay. Okay, how expressions are built. For instance, we have an expression like this: a is equal to t plus within double parentheses b minus a times c. Okay, and how this expression is built. So as we saw that in our last lecture, we use stack, right? Stack is used to implement this. And so we saw that how a stack is used. So in our last lecture, in previous week, for implementing expression, and it also can be used with link with tree. Okay, like a tree structure, you see that this one, it can be implemented with the tree. Okay, so if needed this, we will come later, but let us discuss today our main topics. Our main topics today, we want to discuss binary search tree. Okay, so as we started, how many characteristics of a binary search tree? That so no duplicate element, the right child always will be greater than the root, and the left child always will be less than the root. These are the main topics. These are the main criteria for a binary search tree. Okay, so so let us see the right side one. Is this a binary search tree? Is this a BST? The left one. Is this a BST? How do we check whether it is a BST or not? We need to start all the way from the root, and then we will check over here. 3 is less than 8, so is okay, and then 1 is less than 3, and then 6 is greater than 3 but less than 8. 7 is greater than 6, greater than 3 but less than 8, and 4 is less than 8, so it will come left side, or greater than 3 will go right side, but less than 6 it will come left side. So how they travel from left to right, right to left, left to right. Okay, and this side, okay, this side, is this a BST? Okay, how we cannot ensure that whether it is a BST or not, unless we know what does this actual value means. Okay, it's banana. If we start the first character B, okay, and so if we take the first character, then it may be a BST. So for instance, first character B, You are taking only first character. So the first character A is less than B, so it comes to the left side. Okay, and the first character P is greater than B, so it is going to right character. So B means we are taking the, so for instance here, we know the ASCII value A, sorry, A ASCII value is 65 for uppercase A, and lowercase a ASCII value is equal to 97, and B in uppercase 66, and B in lowercase equal to 98. Okay, and so on. C is an uppercase single quote equal to 67, and C in lowercase will be 99, and it goes this way, right? So P, so this is for ASCII code, ASCII. ASCII values. So in that sense, so P is greater than B, so it is going right side. Now C, okay, it appears C, so it appears C, so C will go the right side of B, okay, then but the left side of P, so it will come over here, okay. C is C, considering C. Now mango, M, so M will be left side of P, and on right side of C, but right side of C, so it will go this way. And then again P is greater than, okay, M, okay, but the question may be here whether this P go over here or go over here. Okay, that is a question. Okay, and then in that case, so since the first character is P, first character is P, first character is P, we will consider the second character also. Okay, the second character is here E, right? So E, and the second character over here is A. So A ASCII value is less than E. So then it will come to left side, and left side, and the first place it got, it will go over here. So papaya will go over here. Now, now again, peach and pear. So pear, where will go in the right side over here or here? So now the first two characters are same. Okay, so we want to consider the first two characters. And then you see that they are same, so we will go to the third character. Third character A, that are same, so we will consider the next character. Fourth character here is C. Fourth character is C, but here fourth character is R. So R is greater than C, so it will go to the right side. Okay. This is how if we consider this, then this is a binary search tree. Does anyone has any question?
Not at this time.
Okay, so let us take our attendance file before I forget. And let us see how many slides more we have. Okay, a few more slides. So this is a BST and this is not a BST. Can anyone please tell me why this is not a BST? Why this is not a BST?
Is it because 7 is greater than 6?
Yes. So where 7 should go actually?
It should be the left child node of 8.
Yes. 7 could be connected like this. Okay. Instead of this arrow 4, 7 your left side of 8. Then it will be fine. Okay. So we can draw like this way, maybe better way. So 7. Okay. Okay, just the ASCII chart. So in terms of complexity, so the depth or height of a BST is big O(n). So we saw that if that grows linearly, so in the worst case big O(n), but for average case log n. So this is a log means with base 2. So log with base 2, some this is written like this: L to LOZ with base 2n is written as LZN. G means with base 2. Okay, and there is a natural log. Say log, the mathematician they use, mathematician mean mathematics use, it is used log, natural log with base e, okay, of n equal to ln. Ln means log with natural. Log with natural. Okay, not n. Ln is natural. Okay. So we will discuss that. I shared the situation where it grows, BST grows linearly. Okay, now. Okay. Two operation for a binary search tree is insertion and deletion operation, right? Insertion means adding an element in a BST, okay, in a binary search tree, and deletion means removing an element, an existing element from a tree. Okay, so the formula is straightforward. For instance, here it is newly added element key. For instance, the element is key. Okay, to a BST will be always is leaf node. It cannot be in middle. It cannot switch any other node. It cannot switch an existing. It cannot push backward or forward an existing node. Okay, it will take always a new position. Okay, the process is recursive. Okay, so what the process is that compare the key, that means the new element, to root. If x is equal to the root, then do nothing. Okay, then it means x is already in the tree. For instance, we have a tree. First, we have a tree that is an empty tree. Okay, there's nothing in it. And then first element we got 10. And we will put that is the root, and then we put 10 over here. Okay. And the next element, if we find 10, the 10 is itself 10. The 10 already existed, nothing to do, because the binary search tree cannot contain duplicate element. Okay, so that what it can do, it can remove the previous value and replace with the new value. Okay, in some perspective it may be useful. For instance, if it contains timestamp, okay, otherwise it is fine. And then the next value, if it is less than the root, for instance 8, so if we can go to 10, after that if we encounter 8, if it is less than the root, then add to the left subtree, and to the left subtree, 8 will be over here. Whereas if it is 12, okay, for instance 10, and if it is greater than the root, okay, then for instance next value 12, we always consider that one by one with the root. We are considering this with the root, and again we will consider this with the root. Okay, then 12 is greater than root, so then it will go to the right side. Okay, and again, for instance, if we are encounter another variable 11, then what happened? Can we do this way? 10, we have already 8, and we can say 11, and we can say 12. Can you do this? Can you do this? Someone please talk to me. Can you do this?
I think we can.
What is the reason? Justify your thinking, please.
Mm, 12 is greater than 11, so you would put it on the right side?
Yes, but we cannot do this. So it cannot replace, maybe a few minutes ago I told you, it cannot replace, it cannot push. Okay, one thing is that you see that this one, the algorithm, it has the process. The new node will always be in the leaf node. It cannot replace. Hold on a second. Sorry for the interrupt. Okay, so a new node always will be a leaf node. Newly added element will always be a leaf node, so it cannot do this. It cannot do this. Okay, what will we say? It will be new. It cannot push. It does not have that much length, that much strength. So it will go the left side of 12. So this is correct. You understand? But this is incorrect. This is incorrect. But this is correct. Okay. Okay. So this way, a new node is inserted in a BST. Now, let us consider we have a few more minutes. Now, okay. So please do this. Do this homework, okay? So practice this at home, okay? So for this one, draw a tree, binary search tree, then apply pre-order traversal, in-order traversal, and post-order traversal. Okay. Now the another operation is find search operation. How do we find an operation in a search operation, continuous search operation. For instance, if we want to find x, an element x, whether it exists or does not exist in a BST. So the find x, return the pointer to the node that has the key x. We need to give the pointer of the node that contains the pointer means address of the node that contains this node. And if that does not exist, then return null. Okay, and then sample is process. If root equal to null, that means if the tree does not exist, then return null. That means the tree is empty. So there is no way that we can find this element in this tree. The tree is empty, so there is no element in it. So there is no scope to search an element. Okay, but same thing and the like insertion. If the element is equal to the root element, then okay, so return the root. Okay, it is the element. And if the element is greater than the root element, then search for the, okay, if the element is less than the root element, then search for the left subtree and recursively subtree. Search the left, further left, again, okay? And if the element is greater than the root, then and search the right subtree. There is a mistake over here. Less than the root, left subtree. If x is, there is a mistake over here. Let me fix it. Not less over here, greater than root element, search right, not left over here, right.
Are we going to take attendance?
Yes. Give me a few more minutes. Let me finish it. Okay. So there are some mistakes over here. Fix it, please. If it is greater than, then right subtree. Okay. So this is the code. How do we write it? We will go to the code in the next lecture. We don't have time today. And another thing is that how do we search? And then right, the last thing is that deletion operation. Deletion operation is a little bit complicated. Okay, one more thing is that we do not delete an element. We just unlink or relink a operation, a value. Okay, there are two ways to delete an operation. One is that called using the right, for instance, okay, let me go. So delete containing node x. For instance, x we want to delete from a BST. So if node x is a left node, so delete it and no other action is required. Okay, but for instance, it says like this. If I want to delete element, okay, so then delete 11. Delete this link. Deleting element means delete this link is fine. Okay, so this is leaf node, 11 is leaf node, delete it. But okay, or in this situation, if 12 is a leaf node, so then you can delete it easily. Okay, but in this situation, in the first situation, if we want to delete 12, we cannot delete 12 because it has its branch. So if we deleting means this link, if we delete this link, what will happen? So this branch will be orphan, right? Baseless. We cannot do this. Or in that case, in the second this situation, if we want to delete 11 in this here, we cannot just remove this. So deleting is a little bit concerning. So for instance, if x has one empty subtree, okay, if X has one empty subtree, that has a empty subtree, then connect the node empty subtree to the parent node and then delete the node. Okay, for instance, if this set in this case 12, we want to delete 12 and it has a one empty subtree, it has this subtree, and then what do you need to do? Connect this with the root and then delete it. Similarly, like this, then connect this and then delete it. Okay, and then another case, if X has non-empty left and right subtree, okay, then see, you need to remember this one. This is the more complicated one. If X has non-empty left or and right subtrees, then copy the smallest value from the right subtree. Yeah, see from the right subtree, this one, the smallest value. Okay, for instance, let me draw it 10. Sorry, I have a few more minutes. 12, and then 11, and then 15, and then 14, and then 20, like this. Okay, then we want to delete, for instance, we want to delete 12. Okay, then from the right subtree, this is 12. There are two ways: either get the lowest value from the right subtree, that is 14, right, and put this 14 over here, 14 over here. So then 12 will be replaced by 14. Put 14 over here. Then 14, and then again delete this one. Okay, so that will then will be 12. Actually 12 got deleted, not 14. 14 came here, 12 got deleted. Okay, this is one way, and there is another way. The book does not say this one, but we can do, for instance, another way. We can take the, if we take the left subtree, then the right value, the greater value for the left subtree. For instance, if we have 13 over here, and 13 over here, so then the greatest value from the right subtree, larger value from the right subtree, we can do that way. We can take 13 over here, replace, and then delete 13. In that case, it can do also. Okay, but this situation, it does not say whatever the book has, right, has, follow only one method. That will be good. So you can follow, you can take the largest value from left subtree or the lowest value from the right subtree. Okay, this way. Follow the book. Book has only one way, so follow the book. That we should be fine. Okay, let us take the attendance. So for instance, deleting this. So I give an example. Okay, so quickly. So in order to delete this too, okay, so it has right, it has sub values, right? That's right subtree. So then whatever value we need to take from the right. So take the lowest value from the right. What is the lowest value from the right? Is 3, right? So 3, then 3 will come over here. Okay, and then again 5 will come over here. 3 will come over here. Okay, 5 will come over here. So you see that 3, and then 4, 3 is moving over here, so then we don't need to 3, and then again move 4 over here. 4 up. Then this will do 4 4. Move this 4 from here to here. 4 is so there. So now actually what is deleted? 2 is deleted. We have already 3, we have already 5, we have already 4, we have already 1. Then what is deleted over here? 2 is deleted. 2 got deleted. Okay. Does anyone has any question? Okay. So removing elements is a little bit complicated than inserting. Let us take that in this way. Okay, let us take that in this. And Jason, Matthew Ashford, Daniel, Barry,
Here.
Antonio,
Here.
Jasmine,
Here.
Treton, Elisa,
Here.
Taylor, Ernest, Angel, Jidan,
Here.
Cody, Isaiah.
Here.
Isaiah here?
Yeah.
Let me see you. Who is Isaiah?
Right here.
Okay. So please be regular in this lecture. We have 5 points. There's 5 points for that is okay. Jimmy,
I'm here.
Savvy,
Here.
Loyal,
Here.
Dave,
Here.
Karen, Mikhail,
Here.
Jack, James,
Here.
Brandon, Noah, Alan, Kenya, Jimmy, Lilivia,
I'm here.
Jesus, Cameron, Sebastian, are you here?
Yeah, I'm here.
Alice,
Yeah, I'm here.
Justin, Daniel, Andrew, Nicholas,
Andrew's here.
Nicholas,
Here.
Jessica. Okay, that's good. So yeah, please be ready for your test next week this time. Yeah. And before you take the test, you know that you need to complete the lockdown setup. But if you have this installed in your computer with other course, then you don't need to do it. Okay, and that's for today. Thank you so much. Yeah, good.
Thank you.
Bye.